In the previous video, we looked at the electron configurations and orbital block diagrams for elements number 1 through 18, and we listed them. Now we're going to go on to do elements 19 through 30. So one thing you may have noticed that each time that we increase the atomic number and go from one element to the next, all we're doing is adding one extra electron. So chemists, just like electrons, are pretty lazy, and we don't want to write all of this out all the time. So for different electron configurations, we can come up with some abbreviations, or we can say condensed noble gas electron configurations. For example, argon here, we've listed in the previous video, and I've written out the electron configuration here. This electron configuration can be condensed and put in brackets. So anytime we have a noble gas electron configuration, we can start with that. And when I put brackets around argon, I know that I'm representing the first 18 electrons in this fashion that we have right here. So when I write out the electron configuration for potassium, I can say argon 4s1. So that's going to say to other chemists, hey, we have 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1. So rather than write out this entire electron configuration right here, I can simply represent that in brackets like this with argon. So the orbital block diagram is going to be very, very similar, and we can just say that for potassium, it's going to be 4s1. For calcium, we can abbreviate the noble gas core the same way. We need to add one more electron, and it's going to be argon 4s2. For scandium, we have the argon noble gas core, and it's going to be 4s2 3d1. So we can give our argon core here, show our 2 4s electrons, and then the next in line is the 3d, and it's going to have one electron in that 3d orbital. For titanium, we have the argon core, then 4s2 3d2. So when we draw our block diagram, we put 2 electrons in the 4s and 2 electrons in the 3d. Vanadium, add one more electron, it's going to be 4s2 3d3. That's going to give us a block diagram with the 2 electrons in the 4s and 3 in the 3d. Chromium, we would predict, based on all of these rules, to have an electron configuration of argon 4s2 3d4. And just when you think you have everything figured out and you're starting to do well in chemistry, we throw an exception at you, because this is not correct, and chromium is going to have an exception to the normal counting rules, or an anomalous electron configuration of 4s1 3d5. And we can kind of look at this based on the electron-electron repulsions, and the block diagram will give us a little more insight as to why this might be. Okay? When we put in 4 electrons in the d orbital, oftentimes a half-filled orbital can give us a little bit of stability. And it's all about how these electrons are going to interact with each other. So if I have 4 electrons written here in this d orbital, and I list one electron here in the s orbital, and we put the other electron here, we now have all of our electrons spin up and there's none that are spin paired. So there's no spin pairing energy cost in any of these orbitals. And we find by representing it this way, with 5 unpaired electrons in the 3D and 1 in the 4s, that it's actually lower in energy than if we paired the 4s, or 2 electrons paired in the 4s orbital and leaving them 3d4. So this is an electron configuration that is an exception to the rule. Molybdenum, which is right below chromium in the periodic table, is also going to see the same exception. Okay. For manganese, then, we now need 25 electrons. Argon is going to give us 18. Then we need to go 4s2, 3d5. So we're right back on track with what we would normally expect from our counting rules. So we need to completely fill up the 4s orbital and put 1 electron spin up in each of the 3d orbitals. For iron, we have the argon configuration. It's going to be 4s2, 3d6. So we put both electrons in the 4s orbital, and then 1, 2, 3, 4, 5, 6 in the 3d orbital. For cobalt, we have our argon noble gas core, then 4s2, 3d7. That's going to give a block diagram with both electrons in the 4s, and then we need to put 7 electrons in the 3d. So 2 of those electrons would be spin paired and 3 of them would be unpaired. For nickel, we have our argon configuration. It's going to be 4s2, 3d8. So we have our argon noble gas core. The 4s electron, or the 4s orbital, is filled with 2 electrons, and we need to put 8 electrons in the d orbitals. So this is going to have 2 unpaired electrons in a nickel atom. Copper is another one of our exceptions. Copper is not going to be 4s2, 3d9. Instead, it's going to be 4s1, 3d10. So when we draw this electron block diagram, we do not fill in the s orbital with that second electron. Instead, we put all 10 electrons in the d orbitals. So our 3d shell is completely filled. For zinc, we have the argon electron configuration, and we have 4s2, 3d10. So the 4s orbital block is completely filled with spin up and spin down electrons. And then the 3d block is also completely filled with electrons. And when we draw these block diagrams, we can see that the number of unpaired electrons is going to vary as we go across the periodic table. And magnetic measurements were some of the reasons why we could prove how the electrons filled in for chromium and copper, and how they were anomalous, or they don't abide by the normal counting rules. So by putting electrons around an atom, we can see over here in these block diagrams on the right how the magnetic properties are going to change from one atom to another, and the transition metals are definitely going to exhibit different properties and different magnetisms as we go across the series here. So this is how we would fill in all the electron configurations for elements 1 through 30. We're going to see the same trends for all of the other atoms in the periodic table, and in the next video we'll discuss how we would write electron configurations for cations and anions.